Welcome everyone to the course on Design of Reinforced Concrete Structures. I'm Jyothirmai, working as Assistant Professor at Department of Civil Engineering, Vienna, VJEC. Today, I would like to discuss about WIT and WIL for DRCS, an initiative by Vienna, VJEC. WIT and WIL expands as why am I teaching and what am I teaching. WIL is student point of view, which refers to why am I learning and what am I learning. This basically a pedagogical framework tries to relate the classroom knowledge to the industrial applications. So as you can see on the screen, there is a building which is new academic block at Vienna VJIT, which shows us various structural components like beams, columns, footings, and slabs. This will allow the student to learn the design of reinforced concrete structures more practically and more tangibly. And this scenario would again be endorsed by the industry, making sure that the applications are well in line with the contents of the topic of concrete structures. Let us see why am I teaching design of reinforced concrete structures. First of all, let us know the importance of this subject. Construction is a major ruling industry in the world, as we know, and it is one of the single largest economy that will help the world be on its highest economical status. And with the increasing demand in construction, number of materials have emerged, starting from the traditional bricks to fiber-reinforced polymers. And out of all these materials, the most commonly used material for construction is reinforced concrete, which is combination of concrete and steel rebars. Here, only concrete if we use, concrete is a brittle material in its behavior and steel is a ductile material as we know. So concrete takes good compression but weak in tension. In order to accommodate this, we are introducing steel as a reinforcement or rebar in concrete, which helps the structure to be safe against compression as well as tension. There are various materials that are commonly used in civil engineering. Let us see a few of them. As you can see, the most common materials that we use for reinforced concrete structures is rebar, fine aggregate, cement, coarse aggregate, and brick, which is usually used for non-structural components. Along with these materials, one more common material that we use in construction industry is different types of steel sections like channels, I sections, angle sections, etc. First of all, why do we need to design? We know that any common structure is made up of major structural components like footings, columns, slabs, and beams. And these are subjected to various types of loads like dead loads, live loads, wind loads, and seismic loads. And these loads, when they tend to act together, the structure may sometimes collapse. So if we design these elements more carefully and precisely, it will give stability and strength to the structure. As you can see, these are the major structural elements in real-time applications and how their reinforcement looks in each of the sections. The first picture depicts beam reinforcement, second depicts column reinforcement, followed by slab and then followed by column. In order to design all this, we need to have a knowledge on the failures that the structures are subjected to. The major failures in structures are due to bending, shear, compression, tension, torsion. As you can see, the first picture depicts a shear failure in a beam. The shear failure usually occurs in a diagonal crack form at 45 degrees. And the second one is a flexural failure in the slab. Third depicts a type of failure in the column, which is buckling. And the fourth one is the most dangerous failure, which is settlement. Settlement occurs in footings. These four components form the major structural elements in any structure with respect to reinforced concrete structures. Then, how do we design and what are the aids required to design these across a given country? Every country has its own code which is followed to maintain uniformity in the design. In India, we follow Bureau of Indian Standards, and for reinforced concrete structures, The code to be followed is IS 456-2000 for plain and reinforced concrete, and for steel structures, we prefer IS 800-2007. Along with this, there are two more important codes to be known by all the students, especially with respect to loads, which is IS 1893 Part 1 to 5, which deals with various types of loads like dead load, live load, wind load, snow load, and any other special loads that comes onto the structures. And with respect to seismic loads, there is a special code which is IS 1893 exclusively for seismic analysis of buildings. So this tells us why we are about to teach the subject reinforced concrete structures. Now let us see what would be the different topics that we would come across reinforced concrete structures. As we have already seen that the major structural components in any structure are beams, columns, slabs, and footings, the contents of teaching would be following in line with the four structural components. Firstly, the first element that we would be seeing is beams, and we will be dealing with limit state method, which is particularly divided into two parts: limit state of collapse and limit state of serviceability. Limit state of collapse deals with forces, moments, torsion, and limit state of serviceability especially deals with deflection and cracking and vibration. Beams come under limit state of flexure. Under limit state of collapse, this is one of the limit state exclusively with respect to bending. As we know, under given loading, whether it is a point load, a uniformly distributed load, or a uniformly varying load, the beam is subjected to bending, which gives us deflection. As you can see in the picture, there is the depth of the beam, and at midpoint, it is subjected to a point load. Now, we have to understand that the beam does not develop same type of stress along its depth in one go. It develops gradually. At the first stretch, the topmost fiber is being subjected to compression, and then the bottommost fiber is being subjected to tension. So as we now see the picture here, we should understand that in a given depth of the beam, few fibers would be subjected to compression and few fibers would be subjected to tension. And our criteria with respect to provision of reinforcement is to take tension carefully. So, in a simply supported beam with this type of loading, tension is occurring at the bottom zone. Therefore, we tend to provide reinforcement at the bottom. I would like to explain more technical terms once we enter into these topics more precisely. And this is how the reinforcement looks in the real beam with respect to stirrups, which will stop shear, and the longitudinal reinforcement, which will take care of flexure. And you can see the cross section of the beam as well with respect to main bars and stirrups. And I'm showing you one more beam with respect to limit state of flexure other than simply supported, which is an overhanging beam. As you can see in the picture, part of the beam is acting as simply supported and part of the beam is acting as an overhang. So in this type of conditions, where does tension occur? If we try to draw the deflection diagram, the beam within the supports will tend to show deflection or tension at the bottom, and the overhang portion, the tension is seen at the top. So in these type of beams, the reinforcement is provided as follows. So in the simply supported part, as we have already seen prior, we provide reinforcement at the bottom, and in the overhang part, since the tension is occurring in the top zone, we tend to provide reinforcement at the top. So in limit state of flexure, we need to understand about where to provide the longitudinal bars, how many bars are required, what should be the diameter to be provided, so that the flexure is taken care without undergoing any kind of failure. Along with bending, one more criteria that beams will usually face is shear. So the picture here depicts the shear failure that can be seen in beams, which will usually come in the form of diagonal cracking at 45 degrees. So in order to arrest shear, we provide reinforcement in the form of stirrups. The stirrups can be either bent up bars, direct stirrups, or inclined stirrups. These stirrups are designed based on how much shear is to be taken care by the beam. And based on that, the spacing of the stirrups is designed, the diameter of the stirrups is designed using the IS 456 code. And the next most important force is torsion. Especially at the corners and at the edges, the beams are subjected to torsion wherever there is reinforcement of columns, beams, and slabs coming together. Torsion is to be taken care with utmost importance, which causes twisting moment in the sections. Usually, torsion does not occur individually, but it occurs in combination with bending, shear, or compression or tension. So therefore, wherever torsion is coming, we need to provide probably additional longitudinal bars in order to overcome the twisting moment. And the next structural element and the most important one is slabs. Slabs also will be dealt under limit state of flexure like beams. Under slabs, we have different types of slabs available, usually which is one-way slab, two-way slab, and continuous slab. These slabs will depend on this longer span to shorter span ratio. The first slab that I'm showing here is a one-way slab. As you can see here, the longer span is designated as Ly and the shorter span will be designated as Lx. If Ly by Lx is greater than 2, we designate it as the slab as one-way slab. In such slabs, the slabs are supported on two sides only, and the main bars will be following only in one direction, and in the other direction we provide distribution bars or secondary reinforcement. In the second type of slabs, which is two-way slabs, here the longer span to shorter span ratio should be less than 2, and in such slabs we see that the slab is resting on all four supports, and therefore the main reinforcement will be provided both in X direction as well as in Y direction. We do not see distribution reinforcement here, unlike one-way slab. The most commonly used slabs in multi-storied buildings is the continuous slab, which will increase the moment capacity of the slab directly. In continuous slabs, there would be negative bending moment developed near the intermediate supports, so we need to provide tension reinforcement near the supports as well. As you can see there, if there are more than 3 supports, we tend to call it as a continuous slab. And the next structural component, which is other than limit state of flexure, the next limit state of collapse would be limit state of compression. This is very particular and is different from beams and slabs because beams and slabs are horizontal structural elements, whereas coming to limit state of compression with respect to columns, it is a vertical load carrying member. With respect to reinforcement in columns, there are different ways in which you can provide, either in circular mode or in rectangular or in square mode. For columns, the reinforcement to be provided is longitudinal bars and lateral ties. Lateral ties will help the main reinforcement to be in position. If you are trying to construct a circular column, minimum 6 longitudinal bars are required, and if you are trying to construct a rectangular or square column, minimum 4 bars are required as prescribed by IS 456. For reinforcement in columns, we design the number of bars to be provided in longitudinal direction, the spacings to be provided in longitudinal direction, as well as the diameter of the lateral ties and the spacing of the lateral ties as prescribed by the Indian Standard Code. In columns, there are 3 types of columns to be taken care. The first column, which is axially loaded or which is having concentric load, that is, the load is going to act through the centroid of the column, as you can see in the picture. In such type of distribution, the load acts uniformly at the center and the column can be directly designed as a normal column. But if we happen to see in a simple design, we come across more than one column. in the plan that I'm showing here. So let me name the columns as 1, 2, 3, 4, 5, 6. Usually, the column number 4, 5, 6 will be under axially loaded condition. But when we talk about 1, 2, and 3, these will be termed as eccentric columns because the load does not act directly at the center. As you can see, column number 1 is eccentric about both the axes. Column number 2 and 3 are eccentric about one of the axes. If the eccentricity of the loading is along one of the axes, I designate the column as uniaxially loaded column, or it will be subjected to uniaxial bending, where the design would be combination of axial load plus bending moment in one direction. If I talk about column number 1, here the column is subjected to biaxial bending, where the column would be designed for axial load plus bending moment in both the directions. In columns, we also have to know one more important topic, which is short columns and long columns, which are divided based on their slenderness ratios. Slenderness ratio, as we all are aware, is the effective length to least radius of gyration. So this value, if it is less than 12, the column would be designated as short column. If it is greater than 12, the columns will be long column or slender columns. Short columns usually fail by crushing and long columns usually fail by buckling. And the last and most important component of the structural elements is the footing. The components that we have seen prior, columns, beams, columns, slabs, all of them stay in superstructure. Footing is a part of substructure, and it directly rests on the ground or the soil. Footing is to be taken utmost care because this element usually fails due to bearing capacity failure or due to differential settlement. As you can see in the picture, that's how the reinforcement of the footing looks like once before covering it with concrete. It's like a formation of a grid. The footing directly rests on the foundation or the soil. There are different types of footings available based on the condition or the location where the footing is being constructed. The type of footing will depend on the type of the soil below. If we are having enough area, we go with individual or isolated footings. If there is a property line coming into picture, we prefer combined footings. Under a wall, we prefer strip footings. For bridges, we prefer pile footings. And if the soil below is having low bearing capacity, we prefer raft or mat footings. Based on this, based on the soil type condition and the settlement behavior, the type of footing would be decided. Footings are to be taken utmost care, which also comes under limit state of flexure. And these topics will be dealt in the coming series or the upcoming topics. And this is why I'm teaching design of reinforced concrete structures. And these would be my topics, what I'm teaching in design of reinforced concrete structures. Thank you, everyone.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.